Welcome to another edition of Comet Algebra. I just love the time that we spend together. It makes me smile. This is the notes for section 10.4, radians and the unit circle. Radians are another way that we use to measure angles. You're very familiar with the degrees, so we want to make the connection between degrees and radians. First of all, where do radians come from? The definition of a radian is that it is the measure of the angle inside a circle of its arc divided by the radius. In case you have forgotten what arc is, or arc length, the arc is from here to here. If you were to take a curve like a tape measure and just measure this curve in inches or centimeters, that's the length of the arc. And we can use this relationship both to define radians and to find arc length. So this isn't really that important to write down. I just wanted you to know where radians come from. And because arc length usually has a pi in it unless we multiply it out and get the decimal approximation. So like if this arc length is, I don't know, pi over 2 about, that's why radians always have a pi symbol in them in the numerator. So what I'd really like you to write down is right here. Arc length is the angle times the radius. But I have found another way to say this that you may or may not like better. To find the arc length, and we'll have some word problems with this in it, because the angle has to be in radians, I just think of this as radians times radius. So that might be a useful way to write down and remember how to find arc length. The next definition is the unit circle. It is simply defined as a circle whose radius is 1 and whose center is at the origin. If you're interested, the equation is x squared plus y squared equals 1. So here's a sketch of a unit circle. I have drawn in the radius here as 1. And we'll be identifying the points where the unit circle crosses over the x and y axes. So this point here is 1, 0, and we'll build on that later. And this picture just kind of shows you what 1 radian looks like. You don't need to know this. 1 radian is about 57 degrees. So this angle represents 1 radian. What I do want you to absolutely memorize from this part is the equivalence between degrees and radians. Since the circumference of the unit circle is 2 pi, we know from our earlier days circumference is 2 pi r, but in the unit circle the radius is 1. So the circumference of this unit circle all the way around it is 2 pi. So this part is what you need to know. And then we can build everything from here. So please memorize that 360 degrees is 2 pi radians, or if you prefer, memorize that 180 degrees is pi radians. If you know one of these equivalences, we can build from there. We need to be able to switch back and forth quickly between radians and degrees, and it is very simple. If you're going to take notes here, just write down this part, that if you have radians, you multiply by 180 over pi, and that'll give you degrees. And vice versa, if you have degrees, then you multiply by pi over 180 to give you radians. Now, you don't need to memorize this because it will be logical. It'll be common sense, and I'll show you what I mean in these following examples. When we're given a convert problem, we know already if we're going into degrees, we know that degree measurements do not have a pi in them, and radians do. Therefore, the pi's have to cancel if you're going to go into degrees. So that tells me I need to have the pi in the denominator here so that it will cancel, and then that only leaves you to put the 180 on top. And then if you multiply this straight across, well, The pi's cancel, 180 divided by 2, so this is 90 degrees. Again here, pi is in the numerator. To get to degrees, the pi has to be gone, therefore I know it's the 180 over pi as my multiplier. Again, the pi's cancel, and if you multiply 5 times 180 divided by 6, or cancel the 6's, whatever you prefer, you would get negative 150 degrees. And this one I just wanted to show you, and we will multiply the pi out this time, or divide it. We'll use it to make an approximation from radians into degrees. So if we had 1 radian, and we're going to multiply that by 180 over pi, in other words, just punch on your calculator, what is 180 divided by pi? And this is approximately 57.3 degrees. When we're converting to radians, we know that we need to have a pi in the numerator when we express a radian measure. So if you'd like to put this 45 over 1 so it looks like a fraction, and then we need to, the multiplier we would choose would have the pi in the numerator because we already know we need that. So just multiply this. Well, I guess I'd prefer to reduce first. 45 goes into 184 times, so in radians this is pi over 4. Likewise, put this over 1. If I'm going 2 radians, I need a pi in the numerator, so pi over 180. And then just reduce this fraction, this 300 over 180, reduce it as much as possible. If I did this right, I got 5 pi over 3. Okay, 138 degrees, same thing, pi over 180. And 138 and 180, if I reduce this right, I got 23 pi over 30. So just remember, radians, you need the pi in the numerator. To get to degrees, you want the pi's to cancel. This next example is when we are asked to find arc length. And I'm just going to remind you from our notes earlier, another way to remember arc length is we take the radians of the central angle times the radius of the circle. So radians times radius. So in our circle here, we're told that the radius is 8 centimeters. We have 2 arcs that we're asked to find, A and B. A, this arc has a central angle of 3 pi over 4. B, this arc has a central angle of negative 60 degrees. So I'm thinking that A is easier because it's already in radians. So we take the angle, 3 pi over 4, and we multiply that by the radius is 8. I'll write that as 8 over 1. And if you multiply that out, 24 divided by 4 is 6. So the arc length is 6 pi. And if we were asked to find to the nearest tenth of a centimeter or hundredth, just multiply 6 times pi, and that gives me an approximate measurement of 18.85 centimeters. All right, arc B has an extra step in it because we are given the angle in degrees. So the first thing we have to do is take this negative 60 degrees and change it into radians. We know a radian measure has pi in the numerator, so the multiplier to pick is pi in the numerator over 180. So if I multiply this and reduce, I end up with negative pi over 3. And I'm keeping the negative sign because we did come down from the initial side. Now we can find the arc length B. We have radians times radius. So I have negative pi over 3 times the radius of 8. I'll put it over 1. Gives me negative 8 pi over 3. And again, if you did the decimal approximation by using the pi key on your calc, approximately equal to negative 8.38 centimeters. Now, the negative sign has a different meaning in this context because the negative 8 centimeter arc length is coming down from the initial side. It doesn't mean that the measurement is negative because we know that's not possible. So we have to take this negative sign in the context given. All right, these last two examples put together things that we've learned in section 3 and 4. We are in the unit circle for both of these. So the steps from section 3 apply. We're going to find the reference angle, draw the reference triangle, label the sides, and do the trig ratios. Since we may not be very familiar with radians, I thought it may be easier to first convert this into degrees. So the pi's cancel, and we have a 30-degree angle. First quadrant angles, they are their own reference angle. So I drew a 30-degree angle right here. We are in the unit circle, so the radius is 1, and hopefully we have our 30, 60, 90s memorized. The short leg is half the hypotenuse, and the long leg is the short leg times the square root of 3. I pause a moment to check what quadrant I'm in to make sure these are the right signs, and in quadrant 1, both x and y are positive. Now I'm ready to do the 3 trig functions. Sine is opposite over hypotenuse. 1/2 over 1 is 1/2. Cosine is adjacent over hypotenuse. So square root 3 over 2 over 1 is just square root 3 over 2. However, tangent gives us a little more challenging ratio. We have opposite over adjacent, so we have 1/2 over square root 3 over 2. Recall, dividing fractions is multiplying by the reciprocal, so I have 1/2 multiplied by 2 over square root 3. The 2's cancel, so I have 1 over square root 3, which needs to be rationalized, so I end up with square root 3 over 3. All right, last example. For the 135-degree angle, same steps apply. Find the reference angle, draw the reference triangle, label the sides of the triangle, do the trig ratios. So I drew the 135, so the terminal side ends up with a reference angle of 45 degrees. Draw the triangle. We are in the unit circle, so the radius is 1. And then to go from hypotenuse to leg on a 45, 45, 90, we need to divide by the square root of 2. So I have 1 divided by the square root of 2. I need to rationalize this. So I end up with square root 2 over 2. And of course, both legs are equal. This is an isosceles triangle. I'll label them both square root 2 over 2. Pause a moment, look at what quadrant you're in, and decide which x is, if the x is positive or negative, and likewise with the y. We're in quadrant 2, so the x is negative and the y is positive. Now I'm ready to do the 3 trig ratios. Sine is opposite over hypotenuse, so I have square root 2 over 2 over 1, which is just square root 2 over 2. Cosine is adjacent over 1, and tangent is opposite over adjacent. So again, I have a compound fraction, square root 2 over 2 over negative square root 2 over 2. But you notice these fractions are the same. When you divide a number by itself, you get 1, and we still have the negative sign. So the tangent is -1. All right, that's a wrap for section 4.